This is Cosmo.
Cosmo is a rambunctious little kid.
A little bit mischievous.
He's smart. A lot of robot in a very small package.
All the technology inside of Cosmo is really there for one reason, to bring the magic of robotic character to life.
It's a very complex system and has 4 transmissions inside of it with probably 40 or 50 gears.
Each robot is made out of over 300 different parts.
There's the AI systems,
The robotics,
accelerometers,
the animation,
gyros,
the computer vision. We're running an extremely complicated artificial intelligence inside the robot, which needs to make thousands and thousands of decisions per second.
He's a mobile manipulator. He can drive around the world. He can see you. He can recognize you.
He looked up at me and his eyes went, whoa. And I was like, wow, he just recognized me.
It gives you goosebumps because you realize that this is a little character who actually understands who you are and what role you play in his world.
Figuring out the path to a unique personality it's an ongoing question.
I think we did about 40, 50 studies on just little nuances, looking at the interface with the monitor where the eyes are going to look at you. Cosmo moves the head and follows you. Every little detail has its special attention paid to it.
We literally have a rigged up version of Cosmo in Maya where our animators can animate him using the exact same techniques that they would use for a digital character. Except the output isn't rendered. The output is actually Cosmo behaving in the real world.
We've been looking for ways to make it either feel more organic, more imperfect, so that it feels more animated.
Rethink Robotics' family of robots operate on the Intera software platform. This revolutionary software does not require the use of a teach pendant or keyboard to program the robot. In fact, you don't program the robot at all. With our smart, collaborative robots, all you need to do is move the arms through the motions to train it how to do a task. You train by demonstration. There are a few simple buttons on the arm and on the robot's wrist. We call it the cuff, which allows you to train a task. On the robot's cuff, there is a sensor which lets the robot know you are ready to work with it. When you grab it, the arm goes into a zero-gravity mode, which allows you to effortlessly move the arm through the workspace, show it what you want it to do, and then it's as easy as hitting run and the robot will go to work. This simple train by demonstration means you don't need to hire employees with special programming skills. Your existing staff can train and deploy our robots. Isn't it time to rethink robot programming?
Games are kind of microcosm of the outside world. That's why games were invented, that's why humans find it fun to play. There's a rich history of computers tackling board games. It started with games like backgammon, drafts, and then finally there was Deep Blue in '97 that beat Kasparov at chess, which was obviously a huge watershed moment for game AI. Since then, the really big remaining sort of holy grail, if you like, has been Go. In chess, the number of possible moves is about 20 for the average position. In Go, it's about 200. Another way of viewing the complexity of Go is that the number of possible configurations of the board is more than the number of atoms in the universe. If you ask a great Go player why they played a particular move, sometimes they'll just tell you it felt right. So the one way you can think of it is that Go is a much more intuitive game, whereas chess is a much more logic-based game. AlphaGo is our program to actually try and crack Go. We played the European champion Fan Wei in a 5-game match. We have an estimate of how strong a program is, but of course you never know. When you play a human player, they do all sorts of very interesting creative things that your programs don't necessarily do. So there's always an unknown.
When we play the first game, I lose.
Interesting. I think he was a bit stunned after the first game, and I think he was unsure as to whether he hadn't prepared enough or whether the program was really strong.
I think after first game, maybe he don't like fight. He like play slowly, so it's why begin the second game, I fight. Do mistakes sometimes. Just give me confidence. I think maybe I'm right. It's why for another game I fight all the time. Now it's complicated. But I lose all my game.
AlphaGo won 5-0, which is the first time ever a program has beaten a professional player. The way I see where we are now is that we've beaten the European champion now, and the next step for us is to try and challenge the legendary player Lee Sedol, who you can think of as the Roger Federer of Go. We always used to talk about, well, if we could eventually crack Go and have a program that could beat the world champion, then we must have invented some generic, general-purpose algorithm. So maybe we're on the cusp of all of that. And we're very excited about it, but it is just one rung on the ladder towards solving artificial intelligence.
we believed that neural networks should work better than the dumb existing technology that's basically just table lookup. And then in 2009, 2 of my students, with a little input from me, got it working better. And the first time it just worked a little bit better, but then it was obvious that this could be developed to something that worked much better. The brain has these gazillions of neurons all computing in parallel, and all of the knowledge in the brain is in the strength of the connection between neurons. What I mean by a neural net is something that's simulated on a conventional computer, but is designed to work in very, very roughly the same way as the brain. So until quite recently, people got features by hand engineering them. They looked at sound waves and they did Fourier analysis and they tried to figure out what features should we feed to the pattern recognition system. And the thing about neural networks is they learn their own features. And in particular, they can learn features and then they can learn features of features and then they can learn features of features of features. And that's led to a huge improvement in speech recognition.
But you can also use them for language understanding tasks. And the way you do this is you represent words in very high-dimensional spaces.
We can now deal with analogies, where a word is represented as a list of numbers. So, for example, if I take the list of 100 numbers that represents Paris, and I subtract from it France, and I add to it Italy, and if I look at the numbers I've got, the closest thing is the list of numbers that represents Rome. So by first converting words into these numbers using a neural net, you can actually do this analogical reasoning. I predict that in the next 5 years, it will become clear that these big, deep neural networks with the new learning algorithms are going to give us much better language understanding.